So now that we've derived the heat diffusion equation, we want to see it in action. So in order to do that, we're going to use explicit differencing to show the temperature profile of this bar as heat is diffused through it. So first we're going to start with the heat diffusion equation. So we have this heat diffusion equation here, and what we want to do is make it into something that we can easily put into Colaboratory code, because we want to solve this numerically. So we can solve the temperature profile as it relates to time and position. So in order to do that, first of all, we're looking only in the x direction. As you can see, we only have this differential distance dx, which means the temperature as it relates to y and z is going to be, there's going to be no change. And we also are going to say that there's no energy generation across each of these differential distances. So all that we're left with is the thermal diffusivity times the second derivative of temperature as it relates to x. It's going to be equal to partial derivative temperature as it relates to T. What we want to do is approximate this so that we can put it into code. So first we're going to approximate the derivative of temperature as it relates to x. So the temperature as it relates to x, we're going to use a certain indexing system of T, J, N, where J is the position from 1 to 20, because we have 20 increments, and N is the increment of time. We'll say that time t is equal to N times the time interval delta t. So using this, we're going to say that the partial derivative of time as it relates to x is going to be t j plus 1 n minus t j n all over delta x. So from this approximation, we now have something that we can index using an array. And so now what we need to do is turn this into the second derivative. So to do that, we just need to take a derivative of this expression. So the partial derivative of temperature as it relates to x, or the second derivative of temperature as it relates to x, is going to be the derivative of this, which is just going to be t j plus 1 n minus t j n over delta x minus t j n minus t j minus 1 n all over delta x. And that whole thing is going to be over delta x. So now we have an expression that relates the second derivative of temperature as it relates to position x, and we can simplify this even further by combining terms on the top. So we know we can combine these delta x's, so everything is going to be over delta x squared, and we'll just have 1 tj plus 1 n. We're going to have two of these tjn's, and we're going to have 1 tj minus 1 n. And so this will be the expression that we use for the second derivative of temperature as it relates to the position x. So now that we know the second derivative of temperature as it relates to position, the only other unknown in our heat diffusion equation is the derivative of temperature as it relates to time. So we're going to make another assumption, or another approximation, similarly to how we did for the position. So we'll say the partial derivative of temperature as as it relates to time. We're going to use the same indexing system of T sub j comma n. So we're going to say the temperature at position j at time n plus 1 minus the temperature at j at position n over delta t. So it's going to be the change in temperatures over the time interval divided by the interval of time. So now that we have both of these expressions, we can plug them into the heat diffusion equation, which I will rewrite. Alpha, second derivative of temperature as it relates to position, equal to partial derivative of temperature as it relates to time. So all we got to do is plug these in. So that leaves us with alpha over delta x squared times t j plus 1 n minus t j n minus t j minus 1 n is equal to t j n plus 1 minus t j n all over delta t. So the first thing I'm going to do is actually move this delta t over to the other side, because what we want to solve for is the temperature at the next possible time. So in order to do that, I'm just going to simplify this term to some variable that I'll call r. And I'll say r times t j plus 1 n minus t j n minus t j minus 1 n is equal to t j n plus 1 minus t j n. So as you can see, we have a tjn on either side that we would like to combine. So to do that, what we're going to do is add this tjn to the other side. And so that's going to give us, let me move up here so I have a little more room. It's going to give us r tj plus 1 n plus 1 minus 2r times tj n plus r tj minus 1 n is going to be equal to the temperature at time, or at position j at time n plus 1. So this is going to give us, using all current times, or using only temperatures at the current time, will give us the temperature at the next possible time interval at position j. And so this is going to be the basis for what we go off and code. Hello. Now we're working on the coding part of this question. So what we want to do is we want to solve this explicit differencing problem using Colaboratory. So the first thing that we're going to do, first thing that we almost always do, is import numerical Python. I'm going to import it as NP, just because that's what I'm used to using. And we also want to make a graph in the end, so we're going to from plotly.subplots import make underscore subplots. So these are just going to give us all the functions and all the Python languaging that we need for this code. So our next step is to set what the values of the constants are going to be. So the first one is going to be alpha, and we know that's 1. dx we know is 1. dt we're going to say is 0.1 for now. And then we know that r is equal to alpha times dt divided by dx, or divided by dx squared. I could get it in there. And then, so these are going to be our constants that go into the r value. We also have a couple extra constants in this problem, first of which is going to be the initial temperature. So the initial temperature of the bar at all points except the endpoints is going to be 20 degrees Celsius. And then we also have a temperature at the endpoint. So at the left endpoint, I'm going to say T left,
and that's equal to 50 degrees Celsius. And then I'll do the same thing for the right end. T right equals 80 degrees Celsius. So these will be all of our constants for this problem. And these basically just give us building blocks on which to build our function. So the next thing we want to do is set the spaces, or the dx increments, basically. So to do that, we're going to use a variable called n, and I'm going to set it to 20. There's going to be 20 increments of this bar. Then for our graph in the end, we want a series of x values. And because we're doing a temperature profile of the bar based on position and time, we want to be able to have those positional points arranged on the x-axis. So to do that, I'm going to do x equals np.arange n. And so what this is going to do is give us a vector of x values from 0 to 19, as you can see there. So the next step is to define our function for temperature. So in order to do that, first we need to make a vector of temperature values. So to do that, we're going to do np.full. It's going to be a vector of length n, 20. And we're going to initially set all the values in this vector to be equal to t naught, because we know all the values except for at the left end and the right end are going to be t naught. So now we'll change the left and the right end to be what they actually are. So because Python indexes from 0, or starting with 0, the left end is actually going to be t0, and that's going to be equal to t left, as we defined up in these constants. And then we're also going to have t negative 1 is equal to t right. And basically what this is, if you want to go to the last, to the last value in like a vector, you're going to index it as negative 1. So it'll just go 1 to the left instead of having to count out exactly how many you have. So now that we have those both set up, we're going to look at what this vector looks like right now. So as you can see, at the very left, it's going to be 50 degrees. At the very right, it's going to be 80 degrees. And everywhere in between is 20 degrees. So this is exactly what we want as our initial value of the temperature profile. So now we can move into making this into a function. So we're going to bring in the function that we derived in the previous portion of the homework and put it into our code. So that function is going to start like this. T, we're just going to start at 1 and then all the way to negative 1. So you might think that this is not going to work because you don't want to replace the negative 1 value, but actually when you slice using Python, it goes up to this value but doesn't include this value. So let's go ahead and look at what that looks like. So yeah, it starts at 1, so we miss out the first 50, and goes up until the last value. So all we have is these inside values right here. So these inside values are going to be equal to r times t at 2, and when you do want to capture that value, it's going to go all the way to the end. You're just going to not put anything after the colon, and so that'll carry it all the way through to the end of the vector. And so we have t2 colon blank here because this is our j plus 1 value. So it's going to be everything 1 to the right of this value right here. So by adding 1 to these, we get 2 and 0. Easy enough. And then to that, we're going to add 1 minus 2 times r. And then this is going to be our new 1, negative 1 value, or our old 1, negative 1 value. So as you know in the equation, we have tjn plus 1 is tjn. So these are going to be the same temperature index values. And then to that, we're going to add r times t, and we're going to start at 0 this time and go all the way to negative 2, because this is shifting all these, or shifting this first value to the left one. So we're going to subtract 1 from both of these values in here. So let's look at what this gives us. As you can see, it's adjusted the second and the second to last values, which is exactly what we want. So now what we're going to do is we want to put this inside of a loop so we can get a constant update of our temperature profile. So we're going to add, or I guess first we'll make the plot. So we'll say fig equals make underscore subplots. And so to do this, we need first our x values, x equal to x, or I'm doing this in the wrong line. So actually, I'm just going to make the subplot, and then fig dot add underscore scatter. This is where I put x is equal to x, and then we'll have y values equal to the t, our t function from here. And then we'll just say the mode is lines. And so this is going to make our graph and update the very first temperature profile. So now we want to make our loop. So we're going to use a for I in range. Let's just start out with 100. Or actually, let's start out with 500. Because I want it to be long enough that we can get what we actually want out of it. So for I in range 100, we want to use our temperature function now, so we can update the temperature values at each of the correct intervals. And so because we have this t0 and t-1 at the beginning of this, it'll constantly update, so it won't mess up our beginning and our ending values despite having this inside of the loop. And then also we want to update this plot with these values that we're going to get in each loop. So we're going to use another loop if I say divided by 10 is equivalent to 0. And what this percent sign function is a remainder function. So we're saying if the current I value divided by 10 has a remainder equal to 0, then we want to add another scatter plot. So we'll say fig.add underscore scatter. And it's going to be using the same values as before. X equals x, y equals t, and we're going to use mode equals lines. And so now if we want to print that at the end of this cell, we're going to say fig.update underscore layout, and we'll just say the width, we'll say it's 800, we'll say the height is 600, and we want the template to have a nice dark background, so we'll say template is equal to Plotly dark. So let's just see what this gives us now. Valid syntax here. Oh, I forgot my colon at the end. So great, now this gives us a range of temperature values, or range of temperature profiles with respect to time. But as you can see, these trace 0 values, they don't really mean much to us. We're going to go ahead and add name equals to an f string. And so what an f string does is it's able to pull specific variable values out of an array using brackets. So we're going to say name fi. And we're going to do the same thing down here. So now we're going to see what this does. So great. Now they actually have specific variables. But as you can see, we have this 499 up here. And what that is it's basically we're having a double of the very first plot. because we're for I in range just 500. So we're going to start for I, well, edit, undo. Let me figure out how to make that go back, and then I'll be right back. Okay, so I was able to get it back. And with one change, this name right here, we don't want it to change with I because it's outside of the loop. So we're just going to make it equal to 0 because it's going to be the very first index entry. What we want to do is we want to get rid of this 499 down here in the loop. So we're going to start at 1 and go to 500 instead. And we'll see how if that fixes our problem. Oh, that should be a comma, not a colon. So great, now we start with plot 0 and go from there. But we don't really want this many plots. So we'll change this to 25. That's much better, it's much more manageable. But as you can see, we don't go until this reaches a steady state. And when it's a steady state, the slope of the line is going to be constant. So what we want to do is we would just want to make more iterations of this. We'll go to, let's say, 1,000. So great, now it looks like we have an actual steady state. And I'll change this to, let's change it to 25, or let's change it to 50. Great, so that's a little bit more manageable. You can see a little bit better how each of these functions reacts. So great. Now we have a temperature profile of this bar with respect to position and time. As you can see, each position is going to be each x value, and the temperature profile, or the temperatures, are going to be the y values. But the thing that we're interested in is how freely we can change r. So in order to change r, since alpha and dx are both going to be the same, always, given in the problem, we're going to change dt. So let's say we want a time interval every 1 second. Let's see how that affects the graph. So as you can see, the graph does not like that. It goes up to x values all the way up to 10 to the 283rd, which is way too hot to be a real temperature that could ever happen. So obviously something is happening that's creating an error, and we want to see exactly at what point that error happens. So we were at 0.1 before, so let's go up to 0.25. So at 0.25 is still all right, so we want to keep moving up a little bit more. We'll go up to 0.5. So at 0.5, as you can see, it's still doing okay. I'm going to change this back to 25 so we can get some more graphs in there. So at 0.5, it's still okay. So let's move up a little bit more. 0.6. So as you can see, already at 0.6, it's affecting the graph. So let's find some ground in the middle. Say 0.51. So this even looks more chaotic. So as you can tell, the cutoff for this R value is going to be 0.5. Anything where dt is greater than 0.5, which makes R less than 0.5, will not work for this explicit differencing method.